In this work, we're going to take a look at the similarity and differences between spatial eigenmodes and principal modes in a short piece of 2 meter graded index multimode fiber, which supports approximately 300 modes or so. This will be the largest group of principal modes studied so far, but it's also the first time spatial eigenmodes and principal modes will be compared. Now, over such a short distance of just 2 meters, you might think that principal modes might not be a significant phenomenon, and you might rather think in terms of spatial eigenmodes, either of this specific fiber in practice or the ideal spatial eigenmodes from textbooks. But it turns out that even on these relatively short length scales, the principal modes are still very noticeable, and in fact they are a much more meaningful description of the way light propagates through the fiber even over just 2 meters. So I guess the obvious place to start is, what's a spatial eigenmode and what's a principal mode? The phenomena of ideal spatial eigenmodes is well known. It's one of the basic phenomena you learn about when you're studying or describing light in fiber optics. So for an ideal waveguide, perfectly cylindrical, no bends, no imperfections, we get those familiar TE, TM, HE, and EH vector solutions, right, from optical waveguide theory. You have these circularly symmetric intensity profiles like this, and those form an orthogonal set of solutions to Maxwell's equations for that waveguide, right, in that geometry. So each one of those modes has its own spatial profile, its own propagation constant, and from that it's also got its own group delay. So an ideal spatial eigenmode propagates through the fiber like so. It has some spatial profile at the input, it has that same spatial profile the whole way through the fiber, and it shows up at the other end exactly the same as when it went in, right? So same spatial profile at the input, output, and all the way through. In the time domain, ignoring any chromatic dispersion, that spatial profile also only has one propagation constant and one group delay associated with it. So it travels through the fiber and all the light arrives at the same time at the other end, so nothing spreads out in time. If you looked at that in the spectral domain, sweep the wavelength of the laser source, then nothing happens. Right? A delta spike as a time response implies it's got a flat frequency response. There's nothing wavelength dependent about the scenario that I've just described, at least to first order. So obviously it can't stay wavelength independent forever. So ideal spatial eigenmodes like this are just as they are described on the tin, right? Ideal. Their behavior is pretty straightforward and it's pretty uncomplicated. But you're also not likely to actually see that behavior for a circularly symmetric multimode fiber in the real world, right? Real fibers, especially those with a lot of modes and a lot of length, and near circular but not perfect circular symmetry, experience mode coupling. So you're probably not going to have a situation like before where light can go from one end of the fiber to the other, staying in the same mode the entire time. Rather, you'll start off in one mode, and then that light will get redistributed amongst many other modes as it propagates, and all those modes have different group delays, so the light will also spread out in time as it propagates. However, the fiber will still have spatial eigenmodes, right? They're a mathematical property of the mode coupling matrix, of the transfer matrix of the fiber. They'll still exist. There will still exist some set of input modes which will appear the same at both ends. Right? They just won't necessarily have been that way all the way through the length of propagation. The mode just happens to have returned to its original state at the other end. But light is spread out in the time domain. So this is really just a coincidence. And if you change the length of the fiber or the wavelength of the source, then you'll no longer have an eigenmode. It just happens to work for that particular wavelength and that particular fiber length combination. Now I've shown the spatial eigenmodes here as circularly symmetric, like in the case for the ideal eigenmodes. But due to that mode coupling and other imperfections in any real non-specialty fiber, that's not necessarily going to happen. Right? The more mode coupling between more modes, the less likely that is to actually occur. In general, you'll end up with two sort of random looking speckle patterns at both ends. And that also raises an important practical question. So these two profiles aren't circularly symmetric, so whether or not they're spatial eigenmodes depends on the orientation of the x and y axis you choose to employ. They're only spatial eigenmodes for that one particular orientation. Now in practice, assuming you're working with a fiber that's at least nominally circular symmetric, how do you even define what the x and y axis is at the other end relative to the input. What does that even mean? But that choice will define what the spatial eigenmodes are. Alright, so let's get a little bit philosophical here. So let's take a look at another scenario. Let's say we've got a fiber like so. We start off with a particular spatial input state. Doesn't have to be circularly symmetric like illustrated here, but that spatial state of light manages to travel almost the entire way through the fiber before it suffers just a little bit of mode coupling right at the end. So like just a once-off event due to a kink in the fiber or something like that. Now the coupling was small and it was near the end of the fiber, so there's not really going to be much spreading out of the pulse in the time domain, and hence it's still going to be wavelength independent. But this isn't a spatial eigenmode now, because it's not spatially the same at both ends. But on the other hand, it sure seems a lot like a spatial eigenmode. It's just that little variation at the end there means that it's not. It is, however, a principal mode. So you should watch my main talk on principal modes to get a more in-depth description of the phenomena of principal modes. But in short, principal modes are wavelength independent spatial states. They propagate with a single group delay. So in that sense, they're like those ideal spatial eigenmodes for unperturbed waveguides, but principal modes can, and in general do, have different spatial profiles at the two ends of the fiber. They're defined in the spectral/time domain rather than the spatial domain, so what they actually look like at either end isn't relevant. So it means that this scenario, just illustrated here, would still be recognized by principal mode analysis. And it also means that you don't have to decide about how you define your x and y axis at both ends of the fiber. In fact, if you wanted, you could just use two entirely different spatial bases at either end, if you wish, right? It doesn't matter. Okay, so with that intro in mind, let's find the principal modes of a 2 meter length of 62.5 micron graded index multimode fiber in the optical C-band, so it's 1530 to 1560 nanometers. We're working here with the GIF 625 fiber from Thor Labs. It's the same fiber as was used in our other paper, Complete Spatiotemporal Characterization and Optical Transfer Matrix Inversion of a 420 mode fiber in optics letters. In theory, it supports up to 14 degenerate mode groups, giving 306 spatial and polarization modes. So in practice, we measure more than that because it's a short length and the behavior is not ideal, so there are some lossy modes that are still propagating. We can still see them after 2 meters. We measure the entire optical transfer function of the fiber using an SLM system in conjunction with the swept wavelength interferometry. 420 modes in, 420 modes out as a function of wavelength. So 32,768 wavelengths from 1525 to 1566 nanometers. And those modes are organized into 20 near degenerate mode groups, at least for the ideal parabolic index case. From that, we can perform the analysis and extract a set of 420 principal modes and 420 spatial eigenmodes. Two different bases, two different ways of representing the same data. So let's have a look at the similarities and the differences. Here we have the results for the group delay and loss for the principal modes as a function of wavelength. The principal modes have been arranged in a way which attempts to make them a bit more intelligible. We've got the x-axis of mode. That's indicated in terms of the near degenerate mode groups of an ideal graded index multimode fiber. So that is groups of size 1, 2, 3, 4, 5, etc. Spatial modes per polarization. So that's each group has 2, 4, 6, 8 modes in it. Modes are sorted by group delay within their mode group and sorted independently for each wavelength. So strictly speaking, the mode enumerated as n at one wavelength may not be the same mode n at another wavelength, because it can actually be quite difficult to work out which modes correspond with which other modes over different wavelengths, because there's a lot of different degeneracies mixed in there, right? So it's hard to pick apart which ones belong to which, and it can also be a bit unstable. We can see that the group delays for the lower order modes start off looking more like the ideal graded index fiber case, staircase with flat steps of degenerate group delays within a group, and then equally spaced group delays between those groups. Then after about the fourth mode group, that breaks apart. Sometimes it's possible to work out something about the refractive index profile of the fiber from the way these break apart. So if you know roughly what the refractive index profile should be and what kind of manufacturing imperfections are likely to occur in practice, you might be able to infer what that refractive index profile is, or at least some of its features. So for example, Here it might imply that the center of the fiber core is much more close to ideally parabolic, but then that starts to deviate at a radius corresponding to the size of those fifth mode groups. Anyway, out beyond the 16th mode group, 272 modes and above, we can see it starts to hit cutoff. You can see the waveguide dispersion kicking in as you approach that cutoff. So for most of those mode groups, the short wavelengths in blue have the shortest delay, and that's dominated by material dispersion. Then in the 16th group, that flips. As modes get cut off, the dispersion is dominated by waveguide dispersion rather than material dispersion. So it can't be seen from this plot, but if you look at what those modes actually look like spatially, it also turns out that modes with more intensity near the center of the fiber are being cut off first. So modes that look more like single large rings are cut off last. So what do those principal modes actually look like spatially? Here's a summary of all of them, all 420 of them in their 20 mode groups. So again, these mode groups would be degenerate if it was a perfectly parabolic index. We've got the two orthogonally polarized LP01 modes at the top, 4 LP11 modes in group 2, 6 mixtures of LP02 and LP21 modes in group 3, etc., all the way down to mode group 20. The slide here is flashing back and forth between what the modes look like at the input and what they look like at the output. There's really two types of modes that stand out by eye. One, we can see there's a lot of single ring-like modes, OAM-like modes, but that look the same at both ends. Those are the kind of modes you'd expect of a circularly symmetric fiber. The other type are these almost Hermite Gaussian looking modes. So Hermite Gaussians of type 0n or n0, which look like a line, sometimes two lines, but there's this preference for an up-down direction. There isn't really much in the way of single line modes in the left to right direction. Probably that one's the closest. You can also see that some of the ring and double ring modes are elliptical in the orthogonal direction. So squish top to bottom, long left to right. So the principal modes here are revealing a degeneracy splitting between the x and y direction, either because the core itself was manufactured a bit elliptical, or it could also be from the fact that the fiber itself was coiled on the table. In any case, that circular symmetry is broken, and that becomes clear in the time domain with these principal modes. Now you'll notice as we go back and forth between input and output here, there's a lot of modes, particularly the circular and Hermite Gaussian-like modes, that look similar at both ends. What I've actually done here is rotate the XY basis definition at the output such that the overlap between the input and output modes is maximized. So that is, I've chosen the XY orientation, which makes the principal modes the most like spatial eigenmodes. And it turns out this exact same orientation also simultaneously gives the spatial eigenmode basis the most bandwidth. So the principal modes become more like spatial eigenmodes, and the spatial eigenmodes become more like principal modes at the same time. So it's reinforcing that this XY orientation is actually a real property of the fiber. But importantly, the principal modes tell you that, and the spatial eigenmodes follow. You're using the temporal properties of the light propagation to line up your spatial axis. Let's zoom in a bit and have a look at some of those principal modes in more detail. Here's an example, which is probably the most spatial eigenmode-like mode out of the higher order modes. It's also one of the ones which looks the most like your standard textbook type spatial eigenmode, circularly symmetric intensity, and almost circular polarization as well in this case, of the same handedness. But I suspect the polarization part is a little bit of a coincidence, because even for a perfect fiber, you'd struggle to maintain that polarization state, because such a mode is actually composed of two completely degenerate modes, right? So it shouldn't really propagate over any distance. So we can look at the plot on the right, and we can see how the output state changes as we change the wavelength. So here, the input state is kept constant, the wavelength is altered, and we see the correlation between the output state at a particular wavelength relative to the center wavelength. And it's nice and flat, just like a principal mode should be, right? It shouldn't change when you change the wavelength. Next up, we've got one of those Hermite Gaussian type modes. It's actually more like an Incy Gaussian type mode, which is a basis that's between Laguerre Gaussian and Hermite Gaussian. It's a line of lobes in the up-down direction, and it's linearly polarized in the left-right direction, and it has a flat frequency response, again because it's a principal mode. The overlap between the input and the output is lower than before. Partially that's because the x and y axis doesn't line up exactly at both ends, but we can see that structurally these two modes are basically the same mode. There's also modes like this, which look similar at both ends, like spatial eigenmodes, but they're not circularly symmetric, nor are they lines. Solutions like this as well, they look like the same mode, but they're actually orientated differently, so they actually turn out to be almost orthogonal in this case. And the bandwidth isn't good either for this one, so maybe it's a principal mode which has become a little bit reorientated somewhere along the travel direction, or maybe there's a bit of another mode mixed in with it, causing it to rotate as it moves, as it travels, and that also gives it a bit of a second order mode dispersion. There's also solutions that just look completely different at both ends. Now these could legitimately look different at both ends. That could be a real property that this principal mode has. But the other thing to keep in mind is if there's a lot of principal modes which have group delays which are too close together for the swept wavelength interferometer to resolve their temporal separation, then they're basically just degenerate modes as far as the experimental measurement's concerned, and the answers you'll get from the analysis are just superpositions of those different degenerate modes, so they could look like combinations. So it could be that these principal modes actually look different at both ends, or it could be that we're looking at a superposition of degenerate or near degenerate principal modes here. So I've got another plot here, which I thought is interesting. It's a representation of the states of polarization of all the principal modes. This is a distribution of polarization states over all principal modes over all space. Here I wanted to see if there's any trend to the polarization. On the left is the Poincare sphere representation. The poles are circular polarization, the equator has all the linear polarizations, and then on the right we've got the rectangular projection of the surface of the Poincare sphere. So red shows the principal modes at the input, and green shows the principal modes at the output. So for example, if we had a mode that was linearly polarized, it would just be a dot on the sphere on the equator somewhere. If we had a circularly polarized mode, it'd be a dot at one of the poles. If we had a radially or azimuthally polarized beam, then it would be a line around the equator because it consists of all linear polarization directions. So here we can see it's a bit of a mess, but it is denser around the equator. So that ellipticity in the fiber we've seen so far is manifesting as a bias towards linear polarization states, which is what you'd expect. In this plot, we've got the spatial overlap of the principal modes at the input and the output as a function of wavelength. So the principal modes have been calculated for each wavelength and the overlap between the input and output measured. And we can see that there's a lot of modes that look like white lines across wavelength. So that is, these modes look the same at input and output, and they maintain that property over a broad bandwidth. So they're like spatial eigenmodes. These are the spatial eigenmode like principal modes. There's also some lines there that seem to trace out a path which is white but it isn't straight. Those represent possibly the same principal mode but at different wavelengths. Its enumeration is different. So for instance, you can see one here near cutoff at 1525 nanometers. It's over there, enumerated as mode 242 or so. Then as it approaches cutoff, its group delay changes a lot relative to the other modes in its group, and it moves out to mode 271 or so. Right? So, but it acts like a spatial eigenmode through that whole transition. It's just its group delay is changing, so its enumeration is also changing. Now, having a look at the spatial eigenmodes. Interestingly, we can still see the circularly symmetric ring-like modes, and we've also got some of those Hermite-Gaussian, Incy-Gaussian type modes, but there's less of them. Why is that? Well, because the spatial eigenmode basis requires that the modes look exactly the same at both ends. So that's both in terms of space, but also in terms of polarization. So for example, with a ring-like mode, if the polarization flips from right-hand circular to left-hand circular, then it's not a spatial eigenmode anymore. And there's a particularly harsh definition, because as I said before, even in well-made fiber that's perfectly straight, it's going to be very hard to stop right-hand and left-hand modes, which are completely degenerate, from coupling. So just like in a single mode fiber, the polarization state will go all over the place due to even the slightest perturbation. But again, the principal modes are not defined in that way. So when you do the analysis, you'll end up with modes that have a lot of the properties you typically associate with real, ideal spatial eigenmodes, but they're not strictly the same spatially at each end. So they follow the spirit, if not the letter, of the law, shall we say. Looking at some ideal spatial eigenmodes here, again we can see some which are a bit like your normal ideal eigenmodes, but also a lot that aren't. And importantly, with all of these, they've got quite a bit of wavelength dependence. So these modes just happen to be exactly the same at both ends of this particular fiber length and wavelength. So change the wavelength, get a different set of modes. They would also be more sensitive to things like temperature. So for a principal mode, the specific spatial properties like the input and output distributions themselves are sensitive to small bends in temperature, but their overall properties are much more robust. So for example, they'll keep the same group delay and the same wavelength independence properties, because that's something which arises over the entire length of propagation. It's not sensitive to small little phase changes. And finally, here we can see a comparison of the bandwidth of the principal mode set versus the spatial mode set. So the measure of bandwidth here is the bandwidth over which the beam maintains 99% spatial coherence. If the output beam is changing a lot, then as you increase the bandwidth of your source, the output will become a mixed state of many spatial states and it will lose spatial coherence. So obviously the principal mode set and the spatial eigenmode set are different. So spatial eigenmode n doesn't necessarily correspond with principal mode n, so you can't directly compare the two modes like that, but they are organized within groups. So between the markings on the x-axis, there you can compare them sort of as a whole, as a group, compare their bandwidth, because they all consist of superpositions of the same group of modes between those vertical lines. And we can see a substantial increase in bandwidth for the principal modes. So up there at 5 terahertz is the bandwidth of the measurement itself. We can see there's multiples of improvement, even order of magnitudes improvement, even over just this 2 meter length. Right? The principal modes really do suppress mode dispersion substantially. In fact, over these short lengths, the principal modes are an excellent way to identify spatial paths through the fiber which don't incur any mode dispersion, and they give you solutions which you wouldn't necessarily be able to guess before you started. We can see that modes near the edge of their group, a lot of those single ring type modes, have very high bandwidth. So for example, mode 419 and 420, those are OAM plus or minus 19 type modes, and as the sole survivors of their mode group, they have no other modes to couple with, and they also, probably because they're near cutoff, have propagation constants which have become quite shifted from the other modes, so hence they have very high bandwidth. So they're kind of like this little island of single mode like behavior out in the edge where there's only mixing between the two different polarizations. Alright, that's it. So we've shown here a comparison between spatial eigenmodes and principal modes, and also shown how principal modes can be used to significantly suppress mode dispersion even over 2 meters of fiber length.